let us begin now with this energy harvesting circuit, and let us see what are the, how should you go about. Okay. Let us take something that is very popular, and we will, as we go along, let us look at other energy harvesting sources, but for to begin with let us start with the solar panel. Okay. Solar panel is the simplest thing that you can think of. Now solar panel, we did mention to you about, I did mention to you about the fact that the solar panel or any of these harvesting devices always have a point at which they provide you maximum power, right. So you recall this thing, we did mention to you about the maximum power transfer under ambient condition. So which means you may have to look at maximum power point tracking systems and chips, which essentially are components which essentially will be useful for energy harvesting applications. Okay, so let us actually see why is that an important thing. What I will do is I will draw something very intuitive. Let us assume that this is time. Okay. This is the time axis. So let me write it a little more clean. Time, this is time axis. Okay. Now what I will do is the output of whatever power conditioning or whatever system that you have done, let us say fixes the voltage to this point, alright, and let us say that this is some 3.3 volt, some output point, some voltage point. Now as the output load, okay, as the output load, this is say, let us say V out, okay. As you keep changing this load, this is the R load, right. As you keep lowering this R load by this potentiometer, essentially the voltage will keep dropping. So you are here, and as you keep lowering the R value, the voltage will keep dropping, right. This obviously is 0 volts. Okay. When does this voltage keep dropping here? As and when the current starts increasing. So let us draw the increasing in current like this. So this is I am sure you all agree, this is nothing but current, this is that I that is flowing, and this is the V out, that is what you are measuring, this is V out. Okay, this is your V out. Just look at this point. There is one point which essentially will intersect both this voltage and current curve, which is a really good optimal point. Anything you do beyond this essentially will not give you any voltage, voltage will go to 0, and anything below you do, you are not completely loading the system, that means you are not drawing sufficient amount of current, which is also an issue, right, because loads do require sufficient amount of current and voltage, sufficient power in order to work, and that power requirements will not be met. Therefore this is that nice sweet spot which you have to keep worrying about, and this is indeed the maximum power point tracking point or maximum power point, right. So any energy harvesting system, any harvesting system, particularly if you are looking at solar or wind or any one of these variable input energy sources, you will have to worry about the IC chip component, which essentially will give you maximum power point, because the input is all the time changing. Clearly it turns out, let me rub this out so that we have sufficient space to talk about other part. Clearly what this simply means is, unlike the LDO and the buck converters we spoke of, where we know that there is a certain V in and then we have a certain V out, input capacitor, output capacitors for stability purposes, we discussed this earlier. This is the LDO. This made an assumption that V in is always there. This made an assumption that V out is with respect to V in being present. But in harvesting circuits you do not even know if your V in will actually be there. Is it there? Is it intermittent? Is it not intermittent? Okay. So, that is the problem. So, unless there is sufficient amount of logic in silicon which makes things smart and assumes that the algorithms such as maximum power point tracking, then assumptions related to very low grade, very low grade I would say, not low, I would say low grade inputs is available, input very low grade assumption related to very low grade input, all of this will have to be made in order to bring out a component which is suitable for energy harvesting. Okay. This is the key point. So, all these things will have to be borne in mind. It is also possible that energy harvesting chips, if you take and you apply V in here, you basically get two types of outputs. One is called the normal V out, the other is called the V LDO. This is typically around the 2.2 volt range, and this could be typically what you connect to the output loads, which is 3.3 volts. Input is low grade, right. If you take a solar panel as a possible input, a single solar panel will measure under bright sunlight conditions, it can give you a maximum of about 0.5 or about 550, I would say. Okay, let me write it as 550. Okay, 550 or 600 maximum millivolt. Okay, and under very low, this is maximum lighting condition, outdoor, right, and it may give even up to about 250 millivolt, just for completeness, and I will say 2.5 volt 0.25 volts as the under the minimum input lighting condition, minimum condition. This would be typically indoor. How to know how much you will get? One is to use a multimeter, the other is to know as an engineer some numbers essentially which will allow you to design your system. Your energy harvesting system essentially may be used, or your embedded system or your IoT system, your IoT device for which you are planning this energy harvesting system could be applied in indoor or it could be outdoor, right. That is what we said. If it is indoor, you should know what kind of lighting conditions exist indoor, what is the amount of light energy why is it not coming well, let me rewrite it, yeah, light energy in the form of light, and what is the kind of lux that is available indoor as well as outdoor. You must know this before you plan anything. For that, use a very cheap Lux meter, okay. And what is a Lux meter? I will show you now. Let us make a measurement, let us see under this lighting condition what is the amount of lux that is being measured. For that, I will pull out this Lux Meter, and you will see that right now it is reading 0. Okay. Then what I will do, I will take this out, this lid, and I will face it against the indoor light that is there. How much is it reading? Yeah, it is reading about 1000 lux, roughly close to 900, and so it is fluctuating between 900 and 930 lux. So just to see whether everything is working well, I will continue to point here, but I will simply reverse this. Okay. This is the element which is actually reading it. So I just reversed it. So if I reverse it, I should get low light, you see, you get 200 here, but then you get some other value, something close to 200, right. Here it is about 185. So if I close this, it should go back to 0. Yes, it is. I have closed it and I open it back here, and so you see about 200 lux. If I open it like this and face it against the light bulbs, I am getting 900 lux. So you see, this is telling you a big story. This is telling you a very big story. Just do not keep the indoor solar panel at some arbitrary position and say I will get 200 lux or I will get 400 lux and I will be happy. That is not the way. You must orient your panels in a manner, your indoor solar panel, in a manner that you will be able to maximize the amount of light energy available such that your electronics will work. What kind of panels do you typically use in indoor, right? That is your next question. So I hope this demonstration was good for you. Simple Lux Meter, it is just available for a few hundreds of rupees. You can buy this and make a measurement before you start your IoT device for indoor applications with energy harvesting, right. That is what we want to do at the end. Very good. So I will put this back and I will show you something more. What I like to show you is the kind of panels that you are likely to use are something. This is a solar panel. You see, this is roughly I would say 2 centimeter cross 2 centimeter, and your IoT device and electronics perhaps will also fit behind this, and let us say it is doing some monitoring of some parameter inside your building or inside your house. It could be some typical some parameter that it is measuring. Clearly you are not talking of large panels which you might have seen in outdoor for traffic signals and all that, where you are talking of a few hundreds of watts that would be required. You are actually talking of milliwatts of power here. Okay. So you can say that this is a theoretically this should give you 2 milliwatts to about 2 milliwatts of power. Okay. I have taken 10% as the efficiency, and I think that you will get about 2 milliwatts, roughly 2 milliwatts if you are lucky, and if it is a good quality panel. Our measurements do not even indicate that you will get 2 milliwatt, you are actually getting much lower values. See, the answer itself is very incomplete, right. What do you mean by saying it will give you 2 milliwatt? It means you will get 2 milliwatt under maximum lighting condition, maximum. What do you mean maximum? Let me go back here. This maximum simply means you are getting a number here, right. This number is something like 200, 300 and all that. Okay, and if I face it, even it is going up to 1000, right. That is what we said, a little more than 1000. It should go to 100,000 it should go to 150,000, it should go to 200,000, and when will you get that? You will not get it indoor, you will get it outdoor. Under good bright sunlight you will get 1,50,000, 150,000 lux or 200,000 lux. If a cloud comes, it will be down to 50,000, it may even be down to 25,000, maybe down to 10,000 lux, okay, that can happen. But you can imagine that that is all fine outdoor. What about indoor? You see, that is what I was saying. If you do this, you get 1000, and if you do this, you are down to 200. Even here indoor you have this problem. So unless you orient your panels properly indoor, you are not likely to harvest in a more efficient manner. Therefore the big takeaway is these panels are all okay, fine, no problem. You may have to ensure that you orient them in a manner that you will be able to extract maximum power and energy from this system. Is this not a tough task? Is this not going to be a, without any knowledge in energy harvesting, what should be my panel, what should be the output voltage that I should get, how do I design my electronic and all of that such that I will be able to get some reasonable output for measurement of my parameter of interest. Well, that is indeed the hard problem, but as an engineer I did mention in one of my previous classes that you should not hesitate to use the free tools that are available on the net. You should never hesitate to do that, you must simulate. So let us see, before you actually buy anything, can you actually simulate something like that, okay, and let us see that whole cycle of trying to do something using your laptop, simulating something and then trying to see in practice whether you can actually achieve it, right. So let us connect all these bullets together, and I want you to actually do it during the course to make your own a little more practice, to actually try out these examples all by yourselves, okay. Let me now switch to the computer, okay. This is my computer, and what I will do is I will start a simulator. Note what I am doing, I am starting a simulator called Ltspice, okay. Let me write it here for you, sorry, why does it not, okay, let us see, let it, so Ltspice, okay. This is from a company called Linear Technology. They have adapted the Berkeley Spice and have released an educational version. This is an educational version, free for learning, educational, obviously it is free. It has a number of models of their LT, of Linear Technologies, a number of the component models are available. Essentially any component manufactured by Linear Technology, you can simulate the circuit, you can do a circuit simulation. Basically this is called circuit simulation. I will not go into detail because simulations are of different types, and this is the most important thing, you are actually doing a circuit simulation. Component that you use will have what is known as a component model, very accurately describing the component's behavior, captured well, and that is indeed the component model. I will not get into the detail because I am sure all of you would have used Spice. Ltspice for instance is also coming from the Berkeley Spice, and different people have adapted the Ltspice actually came from there, and the same spice tool, simulation tool, is actually also appearing in Ltspice. They call it Ltspice because it has a number of linear technologies components. So let us try and open up linear technology spice and just try some energy harvesting energy harvesting circuits, right, harvesting circuits in this Ltspice. Let me show you a very popular energy harvesting chip called LTC3105. Okay. LTC3105 is from Linear Technologies, and you should be able to build a circuit with this. When I say build a circuit, essentially populate the chip pins around the pins of the chip with several passive components. Remember, LTC3105 is a boost converter. Boost converter. Why do you need the boost converter? Because in energy harvesting applications you get very low grade inputs, and in order to ensure that the low grade input is being taken and giving you a reasonable rail voltage of, let us say, 3.2 or 3.3, you should be able to drive the electronics. Okay. Why did I choose this particular component? Well, it goes back to the basic bearing monitoring application, right, bearing monitoring application, which I took as an example, where we were talking about condition monitoring of ball bearings, right, of ball bearings, that use this LTC3105, and therefore let us see if you can simulate LTC3105. Again, I have no bias for a particular company, but just that energy harvesting chips and components, lot of work is actually done by Linear Technology, and so much also with TI and Maxim and other vendors. In fact, TI has another chip called BQ25504, which is also a very popular energy harvesting chip, where the input is also solar as a possible, solar or even thermoelectric generation as an input, and so is with LTC3105. This is basically a DC-DC converter. In fact, most of the energy harvesting chips that you know very well basically form some form of the other, they are basically DC-DC converters, right. They will have, they are nothing but boost converters. They are nothing but boost converters. Please note, go back to what we will be discussing, what we have already discussed with respect to boost converters. There is a usual feedback that you do, output sensing, it is a complete closed loop system. There is a PWM generator, and the PWM output basically drives the series pass element, and the duty cycle of the PWM actually decides the output voltage, right. Input to output is determined by the PWM signal. All this we spoke about. What is special about this boost converter with respect to energy harvesting is the question. So let us see a few simulations with LTC3105 and try and understand its pin layout and so on, and also see how the output behaves with respect to the components that have been chosen, alright. So, this is the background. Let us now move to Ltspice, my screen here, and I will open Ltspice. You can download Ltspice from the web quite easily. You can install it, it is not a heavy file, install it and then open the import the LTC 3105. You see this is LTC 3105. Basically I just went to Linear Technologies website and we downloaded the LTC 3105 and its associated circuit, and we wanted, because we think that before we build anything, before we buy this chip and hook up all these components, you may have to simulate and see whether it is suitable for our conditions. Remember, there is an input, you can see this. I replaced the solar panel with this input voltage source which is going in here, and then this is V out, and this is programmed to give you 3.3 volts at the output. The feedback is available through from the V out back into the feedback pin here. This is a resistor divider network, and essentially it is providing you the required feedback in a manner that the output always remains at 3.3, right, and it also has an LDO at the output. You can see that there is an LDO. So, it is a chip which not only has a boost converter, it also has an LDO at the output, and you have out 2 which is essentially the LDO output, and there is something called P good, which is nothing but the power good, and this is a output pin which you can interface to a microcontroller. This is the P good coming from the LTC 3105 and connected to the GPIO pin of a microcontroller, and use this pin whenever it asserts to see to use additional operations. In fact, this is what we exploit in our bearing application as well. I did talk to you about the this pin in the context of condition monitoring of bearings. So, please look up those that discussion as well. So, that is one thing, and what is also special is this MPPC here, which essentially is the maximum power point control pin, which is doing something very special pin. What is it doing? As I mentioned to you, major difference between a buck boost or a boost converter which is for which is a normal boost converter as against an energy harvesting boost converter is that the fact that the input sometimes can also go to 0, and the output electronics should not be loaded. We said this in the previous classes, in the previous discussions as well. Yeah, so isolation, right, you want to do an isolation so that there is no loading by the downstream electronics, which is a clear indicator that you will need a handle for any loading effect which might happen, and MPPC is essentially taking care of that aspect of ensuring that the output voltage never goes below the so it never shuts down. Basically you should ensure that the LTC 3105 never shuts down and does not get thoroughly overloaded by the output. So, it is in a way providing isolation from downstream electronics. In a way that is what it is trying to do. Which one? This MPPC pin is essentially doing that. What it actually does is, if you take an energy harvesting source such as the solar panel, and let us say I mentioned to you that a single panel can take single panel will give you under good lighting conditions something close to 600 millivolts, and under very low single panel, single cell I should say, single cell, right, single cell. I think we wrote it somewhere, so let us go back, and we did not do that. I thought we had, yeah, it is here, single, oh, so I should use the right word, see this is a mistake. So, let me rub this out, it cannot be panel, single cell. Single cell gives maximum of 600 millivolt under temperature conditions of 25 degrees, and as the temperature keeps increasing this voltage will keep falling down, and that is under maximum lighting condition, and you get 250 millivolt under minimum indoor lighting condition. What this MPPC pin does is, supposing you put 2 cells, suppose you take so let me redraw it, supposing you take very specialize it. So, if you take the discussion on MPPC, what it simply says is, supposing you take 2 solar cells, right, you get 1.2 volts, okay, maximum under good lighting condition. You can set this to 700 millivolts MPPC. In other words, this pin that you see here with this resistors that are here, with this resistors here, this resistor here will actually set the MPPC point to 700 millivolt. I am just giving some examples for you to understand, okay, 700 millivolts. Now, and this is essentially the solar panel, which is supposed to give you under very good lighting condition 1.2 volts, and under indoor conditions open circuit will still give you significant output, but because the lux is poor you can't draw too much power output. Whatever may be the case, this point, this input will never fall below the set point of 700 millivolt. That is the beauty. That means this V out might reach definitely 3.3, but this loading, when there are different loads being connected, when the output of the buck converter is connected to the load, which could include a microcontroller, it could include the radio, it could include sensors, all of that, and there are other power guzzling, power consuming components. It will ensure the electronics there will have to work under the constraint that this input will never go below 700 millivolt, that is what it will do. So, power management algorithm that is running on your microcontroller will have to note that the energy for driving power consuming components will have to come from the capacitor, will have to be delivered through the capacitor after buffering, after storing, and ensuring that once it is stored it has the power to deliver for the power consuming component. This way this input system does not collapse, and with 0 output here. You will never get that situation if you arrest it with this MPPC pin. Okay. So, that is the key understanding here. So, what I did was I replaced the solar panel equivalent component with a voltage source, and why I did that? Because I actually want to show you what I have done in terms of actual implementation. So, let me first run this and you will see what actually happens. This is the output. The input is set to, let me see what the input is set to. The input you can see is set to 1 volt. Okay. So, input is 1 volt. The output here is set to 3.3. It is boosting, there is a load of course, and it is supposed to give you 3.3 at the output. So, let us see. Supposing you want to simulate, just go and press run, right. So, there you are, it has started the simulation. The simulation output is here. I want to see, let us say, this output. I want to see output. There you are. So, you can see slowly it is building, and you will see that it has stabilized to some voltage at the output. And what is that voltage? Look carefully, this output is 3.3. It has actually built to 3.3. So, you can see that the input is 1 volt and the output is 3.3. There you are. This line indicates that the input is 1 volt and the output is 3.3. Very good. Let me also show you the output from the LDO. Okay. So, let me click here. There you are. What is this? This is giving you 2.2, and interesting, right? Initially what will come out will be this 2.2 volts, which is much lower than the 3.3. As you are harvesting the energy here, let me close this. Okay, and actually we should keep this together, only then you will appreciate this. This is the solar panel. Once you connect equivalent of a solar panel, I have just connected a voltage source now, you will get 2.2 straight away, that is this line. This 2.2 you can take and power the microcontroller, start running the microcontroller, acquire the temperature of the bearing, ball bearing, and store that value. Once you get 3.3, how do you know you are going to get 3.3? Because this power good signal is going to tell you that the output will go to 3.3 very soon. After this ramping up period, it will go to 3.3 and stabilize. You will see that you can then switch on other power consuming components and also those components which require this higher rail feed, rail voltage, and complete the operation of sensing and communication as well. All along the input is assumed here that you are getting about 1 volt. okay. So, that you can see is here. Now, let us see, having understood this simple tool, on how you can actually get the required output, what I have done in order to achieve it in terms of practice. For that, I will show you the output of the LTC circuit which I had incorporated into the bearing monitoring part here. Okay. So, let me turn my attention to you here, where the output voltage, which should give you .2. Can you see this? Can you see this output here? Very good. So, first let us see. Look at this. This is input of 1 volt. Recall the simulator. We gave a DC input of 1 volt and we are supposed to get 2.2 volts from the VLDO and we are supposed to get 3.3 volts from the V out, correct. So, let us see those two outputs. For that, let us look at this multimeter. Okay. So, I will show you this output first, which is 2.2. You see that it is 2.16 volts and this is 3.22 volts. This is the close to 3.3 volts. So, what is the big takeaway? The big takeaway indeed is that use in energy harvesting, when you are trying to use energy harvesting technologies for building the power block of your IoT device, do not rush and buy components and start trying. Do not do that. Go structured. Identify what you want to do for your indoor application. You want to try with a solar panel, or you want to try with a thermoelectric generator, for instance, temperature differentials. Let us also try and see if I can show you a demonstration of that as well in the coming times. Okay. So, that is your first thing. You want to know what you want to do, input indoor or outdoor, and after that do not rush into things. Look up several of these energy harvesting chips, components, ICs which are available, and look at the conditions under which they are supposed to work. Is it 200 lux? Is it going to be 1000 lux? What is the input condition, input energy availability? That you have to understand first, and after that you may have to put those parameters that you understood into this nice simulator. Let us turn our attention back here and complete the story, right. You will have to go back and put these values into this simulator. I put 1 volt here, you can see, and which is shown here by this line, which is a 1 volt line. Maybe it may be useful to expand, for instance. Yeah, but it is okay, this is still fine. You can see that this is yeah, maybe I can expand this part very well. Yes, okay. So, this is what we get at the input, and you are getting something close to getting close to 1 volt at the input. Why does it show something else here? Yeah, so this is 1 volt at the input, and 1 volt at the input, and you basically have so let me go back. Okay, so looks like we can try. Okay, let me do one more thing. Close this and resimulate, right? It's much simpler. So run this simulation and see one by one. Input, should be here. Oops, sorry about that. So simulate, I think there's something went wrong. So yes, oh, something went wrong in this simulation here. Sorry about that. So let me close this and restart. File, open LTC, right, simulate. Okay, first is to try the output. Let us see what happens at the output. Slowly building to it should build to 3.3. Yes, it does. You can see that this is 3 volts here and it is stabilizing to 3.3 at the output. Then we have yes, it has stabilized to 3.3, right, and let us see what happens to VLDO. VLDO is at 2.2, that is what we measured, and input is bit noisy for some reason. Noisy for some reason. It should give you 1 volt at the input. So I think I should click it at the right point, otherwise it would give you wrong output. So this is the input, right? So you should actually click it here, and I was clicking it somewhere else and it was showing you all the current and noise that was going to ground. So that is not the right point. So you can see that the 1 volt is the input and output is gone to 3.3, and LDO output indeed goes to 2 volts, 2.2 volts. There you are. What this basically conveys is that you have to do all of this if you are trying to build the power supply block for your IoT device. While I showed you a demonstration of everything that we did, this is true even for non-energy harvesting blocks. If you are trying to use a battery based system also, you should do all this work. Okay. In fact, this simulation is so powerful that you can actually look forward to do the following. And what is that? You can try this by yourself, but you have to connect the bullets that we spoke of in the previous previous class. Let me draw your attention to this thing that I spoke. Charge a battery, charge a supercapacitor, right. Receive the energy when conditions are good, store the energy, and the storage can be in terms of charging a battery and charge a supercapacitor. What prevents you now from trying this little Ltspice simulation by putting a battery at the output or putting a capacitor at the output of suitable dimension and seeing under input conditions of using a solar cell under input conditions of lux, which is about 200, 300, 400 lux, what is the output that you might get? Use that as an input here. Look at how you can connect a battery source, right, to such that you can charge this battery, or connect a supercapacitor and see how much time it takes to fully charge this supercapacitor. All of this, whether a battery at the output or a supercapacitor at the output, all of this can be very well studied by this simulation work, simulation study. And for me, this is a very important thing that you have to do when you are constructing the power supply block of your system, IoT system that you are trying to build. Okay. So, let us move on with these demonstrations to complete the discussion of this chip that we started, this LTC 3105. We took this chip and we have to complete basic understanding of energy harvesting parts which become critical for when you build the power supply using energy harvesting blocks. What are all the things that you have to keep a note on? So, we should complete this discussion on LTC 3105 and close the story on energy harvesting with respect to this chip. See, I started by saying that LTC 3105 can use a small solar cell, and a single solar cell will give you something like 600 millivolt at 0.5 to 0.6 millivolt at a particular room temperature of about 25 degrees or so, right, and it keeps falling as the temperature increases. This is all fine, but you know the thing is that is maximum, that is what we said, right. See, different manufacturers give you different type of solar cells with different fill factors and so many other related. Efficiency is an important point, that is the real story behind a solar panel. My own experience, from whatever little bit I have been looking at how to interface solar cells and solar panels, I normally am a little more conservative in taking the output from a solar panel. Let me draw your attention to what I have written here. In my opinion, you see this particular thing I have written. It is not always true, but you can go by this. If you take a 1 centimeter square solar panel, I think under outdoor condition you should get about 10 milliwatt. The claim by many manufacturers is that you should get even 50 milliwatt. It may be true, and it may often be true that you may get this you may get this output, but for all your calculation purposes, for your dimensioning of the solar panel and so on, you can take this as roughly as what would be suitable for outdoor applications. Come to indoor. For any conservative approach, I would say you must go with something like 1 to 10 microwatts of for this size panel, but the claim again is that you should get up to 100 microwatt indoor. All of this essentially means these manufacturers talk about this conversion efficiency, and I have in my calculations I have actually taken only 10%, which is very conservative. So, I would say this discussion on what is the power output from a 1 centimeter square panel is often going to be disputed. Whatever I say, you will find something better. Obviously, you will not find anything worse than what I am saying. Okay. So, kindly take this a little more carefully in all your calculations, and do not go by what I am saying as the final truth. My experience and my estimations have not gone wrong, because I have considered only something like 10 milliwatt for a 1 centimeter square panel for outdoor, and 1 microwatt to about 10 microwatts. I would say even I have gone up to about 10 microwatt for all the indoor applications. Alright, this is one part. The other part is when I say downstream electronics, you must also note that when I say downstream, this means that there is an ADC, the microcontroller itself is another load. The ADC means there are sensors which are connected to the ADC, they are power consuming components as well, and you may want to do a few tricks before you actually start doing any communication with a typical microcontroller come radio, low power radio like a BLE radio. For any communication purposes, you want to just do some sensing operation like what we said about the condition monitoring, but all of that means that the LTC 3105 itself, when an input is given like what we what we had discussed is a 1 volt input, goes through several phases before you can actually start drawing the power output, either the LDO output for certain operations or actually doing a communication of the sensor value. The first phase that the LTC 3105 is this EHS chip, energy harvesting systems chip, does is it passes through what is known as a startup phase. Then the LDO will go into regulation and will provide you the LDO output directly. Okay. Let me switch to what I mean by this in this picture, which essentially is here, right. This will connect well. So, you can see that this LDO here that you see, essentially where I am pointing to is the LDO output, which is essentially 2.2 volts, right. That is the 2.2 volt point which is here. This one from the chip specification, you can't draw too much power. What you can draw is only about current of about 6 milliamperes. Again, this is what the data sheet says. So, you can at best switch on the microcontroller and perhaps do some basic sensing, that is all you can do with the LDO output. The point really is, why is this coming out first? Look carefully here, this LDO, so this LDO has taken a little more time, because this circuit here that I have put, the components that I have put here is giving you a feeling that the LDO output is settling down faster, slower compared to that of the actual V out, which is actually in reality not true. I leave it to you to actually show that LDO output settles down faster compared to this actual V out. You should actually get that. So, try it. I want you to try and come back and ask me questions related to reversing the role of the V out and this LDO output, which should come to you much faster. Now, going by what you see here, we can still argue that the output has not really stabilized, because you can see that the stability point has come somewhere here. In fact, it is still giving you this little jagged output. I am sure you appreciate why this jagged output comes, and if you go back to what we discussed in the last class, it is purely because of the inductor current, right. This is the inductor which you have seen here, and this is the actual inductor boost converter, and the current flowing through the inductor is actually giving you this wavy nature, and you want it to stabilize. Therefore, you wait until it stabilizes to a good value before start using the output of the regulator. In fact, you can do many interesting things before you essentially conclude on these actual results. For instance, you change this input, okay. You change this input to because it can even start even at 250 millivolt, put it to a lower voltage, see what actually happens to V out. V out actually comes to stability much later. In fact, in some of my experiments which I propose to show you later, the 3.3 that you get here actually comes much later. What you will see is 1.6 volts slowly rising to 3.3 at the output. This can be demonstrated. Meanwhile, the Ldo output which you see here will already come and it will give you 2.2, right. So, that is a nice thing which you can already start using it for switching on the microcontroller and doing other things. This is one thing. Another feature which the LTC 3105 seem to have, this energy harvesting chips normally have, is that under voltage lockout. Okay. Why is this important? Because input power source may be absent for extended periods. When input power, like the ones that you saw here, this input power in this in this simulation picture that I have here, if the input power is this one, this particular one, if it is not there for an extended period, you do not want this output to vanish just because this LTC can now accept power in this direction and ground it, right. You do not want power flow to happen this way and reduce the power output here. So, you want to put this into a complete shutdown state such that the output remains whatever it is. You do not want the LTC to draw power in the reverse direction and bring down the output voltage. This is essentially what under voltage lockout actually is. The converter, this converter chip actually has to do a complete shutdown, as I have written here, in order to ensure that the chip is indeed stable. Finally, I want to draw your attention to this little story that many of the embedded systems electronics that you will be working on will actually be drawing. If you take the LTC output that we have seen as 3.3 volts, and if you do sort of a communication, you do some sensing, compute and then do a communication, you will need anywhere between 20 to 35 milliamperes for a very short duration of 1 to 4 milliseconds, which gives you a power consumption of about, power requirement, not consumption, power requirement of about, in fact it is indeed consumption, right, about 70 milliwatts or something like that you might need. If you put the microcontroller to sleep, your sleep currents are typically 4 microamperes. You may need anywhere between 12 to 15 microwatts of power, right. So, this power requirement of peak power requirement of 70, sleep power requirement of 15 milliwatt, all of this leads to deciding what should be the size of your panel, right. So, that is what I wanted to drive home, that your sizing of the panel will largely depend on how you design your power management algorithm. Energy harvesting systems means sensors means this is a very important requirement. You must design your power management algorithm, and indeed the bearing condition monitoring of ball bearing essentially was doing that. I had discussed the flow chart with you, which you can now see is a very important, it really fills up all the gaps in what we discussed. Thank you very much.